Alright, so here we have a pretty fun problem. We have the integral, and it's just an undefined, indefinite integral, and it's the square root of x over 1 plus x cubed in terms of x. So let's rewrite it here first. 1 plus x cubed. Now with especially ones like that, I want you to be very instinctive, okay? Meaning I want you to listen to your thoughts very closely, okay? So again, mathematicians are lazy. Mathematicians are very, very lazy. They never want to do a problem. They want to do a problem that's super similar and much easier, okay? So they want to do the bare minimum amount of work. Look at this problem here. Wouldn't it be much easier if you had the integral 1 over 1 plus x squared? Wouldn't your life be amazing if that was your actual problem? Because you know that integrates to just arctan of x. Everyone knows that. Or at least, I hope you do. Now you do, if you didn't. So, instinctively, I think that was, or hopefully it is, your first thought. This looks too complicated. There's too many little small things. There's square root of x, there's x cubed. It's all unnecessary. I just want to do this. So, let's actually make a few transformations to this function and make it look just like that. Or maybe as close as we can. First of all, I'm going to say let u equal to the square root of x, okay? Again, the square root of x is sort of our reason why we can't do this problem. It's sort of that one limiting factor. It's sort of complicating the entire problem itself, right? So we find du is equal to the square root, or 1/2 times 1 over square root of x. So what do we do from here? This is also can be written as dx over 2u. Du is equal to 2u dx, right? So let's substitute that into there. First of all, what do we get? We get the following. U over 1 plus x cubed. What would x cubed be? Well, first of all, u is equal to the square root of x. Thus, x is equal to u squared. Now, you could also say something happens with this because it becomes plus and minus. Let's just take the absolute value of x. Because again, yeah, you would have to a few things and account for other things. Just assume that x, plain old x, is equal to u. Thus, u to the power of 3, or x to the power of 3, is going to be u to the power of 6. Okay, and then again, we said that du is equal to dx over 2u. In other words, what do we get? We get 2u du is equal to dx. So let's plug that into there. We get u times 2u du. Okay, first of all, let's factor out that 2 and square the u's. We get now u squared over 1 plus u to the power of 6 du. Immediately, I might say, let's do integration by parts. But of course, the second we try to integrate by parts, we see that we'll get u squared, then 2u, then 2, right? But the thing is, we can only integrate arctan once. We get 1 plus u to the power of 6, right? Then you'll get 1 to the power of u cubed, right? But then I don't wish anybody to memorize the integral of arctan. That's crazy. Let's not do that. Let's do another something. Let's instead do let v equal to u squared. Okay, what does that give us? That gives us dv is equal to 2u. We can't do much actually. Let's do something else. Let's instead make v equal to the u cubed. dv is equal to 3u squared. Now we're getting somewhere. Okay, now we're getting pretty close to something. So that means u squared du is equal to 1/3 dv. Amazing. So let's make that substitution here. We get instead now 2 over 3 to bring out that constant. U squared gets directly substituted. I get dv here. Now, if v is equal to u squared, then v squared is equal to u to the power of 6. Now look at that. With a few transformations, we've made this problem exactly what we wanted. We made it into that simple arctan integral. So just as mathematicians do, we were lazy and found a simple equivalent problem. So again, we did the first substitution in terms of the square root of x. Okay, substituted everything in. And then we found that if you had done v is equal to u squared, I would have gone dv is equal to 2u du, which would give me another problem, okay? Because then I have to express u in terms of v, which would be the square root of v. And then again, we're doing circles, okay? So instead I did something that would have a derivative of u squared times some constant k, okay? That's what I was looking for. I want something that once you differentiate it, gives me u squared, so I can directly substitute this here, okay? Which I know would just be u to the power of 2 plus 1, which is u to the power of 3, right? Because it decreases by 1 power when we differentiate it. Thus, I chose v to be u cubed. Now we can directly integrate this with no worries about the bounds. I get arctan of v. Okay, now we make our substitution back in. What was v? Well, v was u squared, right? So let's bring back, what was the previous color? Okay, so v was u squared, so let's put u squared here, right? And no, oh sorry, it was u cubed. U cubed. Okay, now, what was u? Because again, this integral was in terms of x. What was u? U was the square root of x, okay? So I'm going to do a bit of a shortcut here. 1/2 times 3 is 3 over 2, which means I'd have x to the power of 3 over 2. Amazing. And that would have been the same if I'd just done square root of x to the power of 3. Same thing happens, just the multiplication of powers. I'll delete that here. And of course, the almighty variable that all of us forget, especially on our exams, plus c. Don't ever forget plus c. And that would be your final integral of what? Of this monstrous looking function. And of course, with bounds, you might have to check a few things. Here we didn't have any bounds, but if this had been a definite integral, first of all, what do you want to check? You want to check that this denominator never becomes 0, okay? So this denominator cannot be 0, which means that x cubed cannot be -1, and thus x cubed cannot be the cubic root of -1, so thus x cannot be -1, or of course, if you want to go complex, cannot be omega or omega squared, okay? Depends on what domain you're doing this on top of. We'll say for real solutions, x cannot be 1. But of course, you want to check omega squared for complex solutions. What else can you check? Well, actually, the fact that we can't have -1 is already sort of seen by the fact that we have square root, okay? Because the square root function cannot have anything less than 0, okay? X must be greater than 0 for the square root of x to be the element of the real numbers. So again, that's sort of a requirement unless we're doing complex analysis. Then, of course, I'll put this in orange then. We need the complex omega and omega squared. Yeah, well, that's basically it. Cool. Hopefully that helped.